In this module 8, we are going to be talking about prediction in the context of stochastic models and observations corrupted by noise. Everything is stochastic. Again, here we are having a stochastic model which could be linear, nonlinear. We have a noisy observation which could be a linear function of the state or nonlinear function of the state. Again, one can consider 4 different possibilities, model being linear, nonlinear, the observation being a linear function of the state or nonlinear function of the state. I am going to start with the simplest possible case where the dynamic model is discrete time linear model. The observations are linear functions of time. The model is not perfect. The imperfections in the model are compensated by some random input. We will talk about the properties of the randomized input that is meant to compensate for the deficiencies in the model. The whole aspect of data assimilation, assimilating noisy observation into stochastic dynamic models, is what we are after. The data assimilation algorithm, ultimately when we derive it, is called the Kalman filter equation. So the name filter in Kalman filter has a very special connotation. We will talk about what is filtering, what is prediction and so on a bit later, but we will start with some of the basic descriptions of the model of the observation. The Kalman filter also refers to sequential state estimation. You may recall from our discussions with static deterministic estimation case, we can have an offline or an online estimation techniques. Online estimation techniques are also called sequential state estimation. In the sequential state estimation, things keep moving forward. In the 4D war, on the other hand, the adjoint takes you back. 4D war methods are in general offline are all offline techniques. So this is an alternative to 4D war where there is no going back, everything keeps going forward. The estimation, the inverse problem, everything is solved sequentially, much like we had a recursive linear least squares in the context of static deterministic problems. So the model is a discrete time stochastic or random model. This is the general description of the nonlinear discrete time model we have already seen. M is the model map, M is from Rn to Rn, Xk is the state. This is the example of a nonlinear map. This is this is an example of a linear system. The addition of noise is new here, Wk plus 1. Wk plus 1, so let us talk about the timing diagram and this is little bit of a notation. This is time k, this is time k plus 1. At time k I have known xk. I would like to know the state at time k plus 1. The model maps xk plus 1 to m. So m is called one step transition map if it is a nonlinear function. It is called one step state transition matrix if it is a matrix. This is the matrix in the linear case. This is a map in the nonlinear case. We use the same symbol m. The junctor will tell whether it is a matrix or a map. The Wk plus 1 is the noise. Wk plus 1 is the noise that occurs after time k before time k plus 1. That means I know xk, I would like to be able to compute xk plus 1. If there is no noise, xk plus 1 would have been m times xk or m of xk depending on the models, linear or nonlinear. So xk plus 1 is a sum of what a deterministic model would have given you plus a noise that comes after time k. So to emphasize the importance of the noise coming after time k, I am going to denote it as Wk plus 1. So Wk plus 1 is the noise that affects the evolution of the system given xk. The noise occurs after time k, before time k plus 1. So xk plus 1, the value of the state at time k plus 1 is the sum of the deterministic part plus the random part. That is the interpretation for making it Wk plus 1. In some textbooks you will see Wk plus 1 is called Wk. Really it does not matter. We thought, in order to make it very clear, that it is the noise affecting the system after the state k is known. It provides less room for confusion. So Wk, what is that? It represents a compensation for the model error. It is also a random process. One of the simplest of the random processes one can think of is white noise. What is white noise? W1, W2, W3, this is the sequence of noise that affects the system. We say W is the white noise if there is no temporal correlation. What does it mean? Expected value of Wi, Wj transpose is equal to 0. In other words, if I and j are two distinct moments in time, if I am considered the noise Wi and Wj, they are temporally uncorrelated for all I not equal to j. So that is what is called white. So is a sequence of uncorrelated noise that affects the evolution of the system. You may so xk is the true state. I do not know that, so I am trying to add a noise to make up for the deficiency, and M could be a matrix or M could be a map. Now you got all the things associated with the model. With respect to the observation, again nothing changes, essentially the same. This is the nonlinear function of the observation, the linear function of the observation. I am trying to do both of them simultaneously because we have gained a lot of expertise in trying to handle linear nonlinear observation models and other things. H is a map, H is a matrix, covariance of Vk is 0, covariance of Vk is Rk. I am sorry, covariance of Vk is Rk, mean of Vk is 0, and Vk is, again I should have said this is Vk is Rm, sorry, Rm. So Wk is the model noise. Wk belongs to Rn. Vk is the observation noise that belongs to Rm. Hope the description of the model and the observations are clear now. Now I am going to talk about the technical definition of the word filtering, smoothing and prediction. This definition is due to Wiener. This definition is also due to Kolmogorov. These kinds of definitions have been introduced in the literature since early 1940s. Wiener 1942, Kolmogorov 1942. As I mentioned when I was doing optimal interpolation, Wiener and Kolmogorov independently were thinking of the same problem. Wiener was working in frequency domain, that because he was an expert in Fourier analysis. Kolmogorov on the other hand was working in time domain. So except for this difference in the domain of interest for analysis, they essentially uncovered the same set of results. So let us give a technical of what filtering is. In what sense the word filtering is used in Kalman filters. In general, colloquially, filter means something that stops from certain things going out. For example, if I have a radio, the radio has a tuner. The tuner essentially filters out all the signals that does not belong to a particular spectrum. So we can call a low pass filter, a high pass filter, band pass filter. We talk about coffee filters. So we know in what sense filtering in an ordinary sense is used. Now technically filtering has a slightly different connotation. So let us talk about that now. Suppose I observations from in the interval 1 to n. The observations are Zi. Let us assume the observations are coming in discrete instances in time 2, 3, 4, k all the way up to n. Let Zi, I running from 1 to n, be the collection of observation. Let us call the collection of observation as f of capital F of n. N is a subscript. N denotes the number of observations that we have. N also denotes the last instant we have the observation. So given a set of observations Z1 to Zn, if I want to be able to make a prediction about the system, let me do one thing. I don't want to put a k here. That's right. That's right. If I want to be able to talk about the state of an estimate of the state of the system at time k greater than n. Please understand, this is the time interval over which I have the observation. I want to make an estimate of a state of a system at a time k beyond n. At a time k beyond n. That problem is called the prediction problem, as you rightly know. As you rightly know. So x bar k is the estimate of a state of a system at a time in future. How do I tell the time in future? K is greater than n. So you can think of n as today, now. If k greater than n means it is the future. So given all the information up to now, trying to estimate the state of a system at a time in future, that is the prediction problem. That is the definition of prediction or forecasting. Knowing what I know today, what will be the price of an IBM stock tomorrow, that is a prediction. Knowing what I know today, what will be the temperature distribution in early spring in North America, that is a prediction problem. So on the other hand, suppose I have known all the information from 1 to n. I want to go back. I want to be able to evaluate the state of a system xk for some k less than n. That means I have the benefit of information from 1 to n. I am still trying to go back to estimating a quantity at a time k less than n. So k less than n means past, k greater than n means future. Estimating a quantity in the past when k less than n, that calls smoothing, because I have the benefit of the entire observation 1 to n. I am interested in trying to find an estimate at a time k in between 1 and n. I am allowed to exploit all the observations, and that problem is called smoothing problem. So prediction problem, smoothing problem. If I want to make an estimate at the time k is equal to n now. So what is the idea here? I have been given a bunch of observations from 1 to n. I would like to be able to get a state of the system at time k is equal to n. That is called the filtering problem. So filtering problem is an estimation problem where I use all the information up to the time n, and at that time I would like to be able to get the best estimate. That is the filtering problem. Smoothing problem is given a set of observation from 1 to n, I would like to be able to estimate a state at a time in the past. Prediction problem is trying to estimate a state given the set of observations at a time in the future. So what is given to you, what you want to estimate, what is the relation of the time index at which you want the estimate to be, depending on the relation of the amount of observation available and the relative relation of the time index k with respect to n. N is the last time at which the last observation is available. We have 3 problems: smoothing, filtering, prediction. So filtering, smoothing, prediction are 3 classes of problems. This is a classic definition, widely accepted. This is due to the pioneering work of Wiener, and these classifications are known since early 1940s. So what is the problem of Kalman filtering? That is what we are going to talk about. We are going to assume everything is linear. Everything linear means what? So let's talk about this now. I also want to take one more moment to talk about the problems the problems related to the models. So we talked about the model being stochastic. Let us consider the linear model. Xk plus 1 is equal to m times xk plus wk plus 1. Wk plus 1 is the white noise. Therefore, xk plus 1 is also random. This is a model. Every model needs to have an initial condition x naught. I am going to assume even the initial condition is random. The initial condition is picked from a realization from a prior, you can think of that as a prior distribution with a norm which is normally distributed, m naught as the mean, p naught as the covariance. So initial condition is random. So if there is no noise, if the initial condition is random, the solution is random. If the initial condition is deterministic and if there is a noise affecting the model evolution, then the model solution is random. In here I am considering the two sources of randomness that affects the state of the system. One is the randomness in the initial condition, another is the randomness in the noise. So the noise that affects the system, the noise that forces the system, the initial condition that is random, the observation are noisy. So if I did not have noise, analysis of a dynamical system with a random initial condition and random forcing, that is called analysis of stochastic dynamical system. So I need to be able to first understand analyzing the properties of stochastic dynamical systems, how I can characterize the evolution of the state, or what are the probabilistic properties, how do I characterize the probabilistic properties of the state. That is the first task. The second task is, suppose I give you on the top of it observations, how do I bring in the observation in addition to the stochastic model analysis to be able to combine the model and the observation to get an analysis. So the model solution is now going to play the role of background. Observations are going to still play the role that it has played all along. So the model forecast playing the role of a background provides the prior. The observation is going to provide you the new information. We are going to combine them, so you can think of Kalman filter again within the Bayesian framework. So there are three sources of randomness. Initial condition is random, model forcing is random, the observation noise is random. We are going to assume that all the three noises are uncorrelated. So what is the basic idea? Given a set of observation fk from time 1 to k, find best estimate of x hat head of xk. Look at this now. I am given k observations from 1 to k. I want the best estimate x hat k. You can see from the previous slide, this is the filtering problem. So x hat k is the filtered estimate. What is the characterization of filtered estimate? That minimizes the mean square error. Again, least squares. The magic of least squares comes again and again and again. It's inseparable. So what is the idea here? Xk is unknown, xk hat is the estimate, that is the error in the estimate. So xk minus xk hat transpose times xk minus xk hat, that is the covariance of the error. I'm sorry, I shouldn't say the covariance of the error. This is the inner product of the two anomalies. I'm sorry, this is the sum of the variances of all components of the forecast of the filtered estimate, and that is essentially given by the trace of this matrix. A bracket is missing. So this quantity is inner product as a scalar. This scalar is equivalent to trace of the covariance matrix. Please realize this is the covariance, that's the trace. So that is equal to trace of I shouldn't say this. I don't think this is correct. I'm sorry. So that trace is enough. So now we have stated the problem. I want an estimate xk hat of xk such that it minimizes this mean square error. That is the statement of the problem. Because I have given all the information up to k. If because I am interested in estimating the state xk, this is also called filtered estimate. Xk is called the filtered estimate, or the estimator that estimates xk hat is called the filter equation. That is where the notion of filter comes in. If I also can show that this filtered estimate is unbiased, we have already seen minimum squared error is equal to minimizing the variance if the bias is 0. We have seen this relation when we talked about the Bayesian setup. Therefore, it is very prudent to analyze and arrange things such that the estimate not only minimize the mean square error, it is also unbiased. These two combined together will give you the minimum variance estimate. Now please understand, we are not now talking about linear minimum variance estimate. We are not bringing linearity right now. We are simply say I want to have a minimum variance estimate. Linearity refers to the structure of the estimator. So that is I want the best. That's exactly the whole idea in here. I also want to bring out one more. This problem is called linear quadratic Gaussian, LQG. Is a lethal combination. Linearity, the model of the observation. Quadratic nature of the objective function to be minimized, and the Gaussian nature of the noise involved. Kalman first showed this LQG combination is the lethal combination. Lethal in what sense? We can get absolutely beautiful results. It is one of the very few cases we have absolutely beautiful results. So one can ask yourself the question, well, seldom in life is linear, why are you barking on linearity? The problem is, well, nonlinear problems are hard to solve. Anyway, I can't solve them, I can only approximate them. So mathematically it's interesting to ask a question, which problems are solvable in closed form and what are the properties of the solution? At least I want to enjoy the moment. So the moment of enjoyment occurs when you deal with LQG problem. So in the literature on control theory, actually Kalman was a control theorist. Kalman introduced this within the context of control theoretic arguments. Therefore, within the context of control theory, LQG theory is a very famous, very popular, very fundamental theory, and this is an instantiation of the beauties of LQG. So before I talk about, where are we? We described our model. The model has two sources of randomness, initial condition and the forcing. Observation has another source of randomness, which is observation noise. Given a bunch of observation, given the evolution of the dynamical state, I would like to be able to estimate. So given the observation, also given the model information, I would like to combine everything, whatever you can do, give me the best estimate in the sense of minimizing the mean square error, which in addition, if I add the concept of unbiasedness, also gives you the minimum variance estimate. That is the problem we set out to solve, and that problem, when everything is linear, is called LQG. So I would like to separate the thing into two phases. First is model analysis, model forecast analysis, or model forecast step. Let us take the baby step 0 to 1. Once I understand what goes from 0 to 1, then I can go from k to k plus 1. So let us consider the transition from 0 to 1. Please recall, my initial conditions are random. I have assumed the initial conditions comes from a normal distribution with the mean m0 and the covariance p0. Now I would like to be able to separate several quantities of interest to us. Xk is the true state. Xkf is the forecast of the is a forecast estimate of the true state. Xk hat is the analysis. So this is the analysis, this is the forecast. So these are the two quantities we will go back and forth. Xk is the state of the system. So Xk is the state of the system, This is forecast, that is analysis. So initially at time 0 I do not have any observation. The only information I have about the initial state is that it is normally distributed. Therefore, what is my initial analysis? My initial analysis is the mean of the initial distribution. So what is the initial analysis covariance? Pk hat, that is equal to P naught. Please understand, analysis supposed to represent the best information I have. So initially the analysis contains only information derived from the initial condition. If you give me a Gaussian random variable as an initial condition, what is the best estimate of the random variable? Is the mean. What is the best estimate of its covariance? The covariance of the underlying distribution. So I am now going to postulate the initial analysis x naught hat is m naught, initial analysis covariance p hat naught is p naught. That is exactly this statement as well as this statement. Once I have initialized the analysis and its covariance, I want to be able to generate the forecast. I want to be able to generate the forecast. So I would like to be able to now use them. So okay, again there is no observation now, only model. Knowing what I know at time 0, if I feed this information to the model, if the model gives me an output, how do I generate the forecast from the model output? Knowing that the model output is random. That is the question. This is what is called stochastic dynamical system analysis. So given x naught, I want to be able to compute the prediction of the state x1. So x1 is the state of the system, x1 is going to be a random. So I would, okay, when I am trying to talk about predicting a random phenomenon, I need to think about decomposing the random process into one of two things. There is a deterministic or a predictable part, there is an unpredictable part. We can only control the predictable part, unpredictable part we have no control. For example, the noise by its very nature is not predictable. Therefore, what is that I am going to define now? Again I want to bring out one more fact. When we did the mean square error estimate, what is the theorem we have proven? Within the mean square error analysis, the best estimate is the conditional mean. We have already shown that. Therefore, I am going to want to create x1f. Please understand my notation. What is x1f? x1f is the part of the forecast of the state at time 1 that I have control over. That is the predictable part, and that is equal to conditional expectation of x1 given x naught hat. What is x naught hat? X naught hat is the information about the initial state. Who is going to create x1? Model is going to pull the x naught hat into x1. x1 is the true state of the model. The true state of the model according to the model equation is m naught x naught plus w1. Now I am going to talk about one more little thing. You can write the model equation like this: xk plus 1 is equal to m of xk plus wk plus 1. I can also write the equation to be mk of xk plus wk plus 1. In star, so this is double star. These are all important things, that is why I am trying to spend little time. Both are linear, but in here m does not vary in time, here m varies in time. The algebra, the mathematics of it is not much different between m varying in time, m invariant in time. So I am assuming I am sticking a k to m. So what is double star mean? I have a linear time varying model. If I can analyze the linear time varying model, the time invariant model is simply take the k out of m. So without loss of generality I can assume the model is time varying, therefore m0. So if I am using my model to be a time varying model, x1 is equal to m naught x naught plus w1. That is the model equation. Please go back to my model equation earlier. That is xk plus 1 is equal to m of xk plus wk plus 1. For simplicity to get started, I assumed m is a constant. Now I am sticking m sub k. M sub k essentially refers to the fact that model could also be varying in time. The algebra is no different. If I can get a free ride, why not? I would like to get the maximum benefit out of it. So if I use the model, this is what the model will tell you as where x1 is. I'm sorry. This is what the model will tell you as where x1 is. But x1 is random. What is the estimate of x1? Conditional. What is the best estimate of their true state? Conditional expectation. So conditional expectation of x1 given x naught hat, that is equal to m naught of x naught hat. Because look at this now. Conditional expectation of, so conditional expectation of a linear operator. Conditional expectation of a sum is the sum of the conditional expectations. The second conditional expectation is expectation of w1 with respect to x naught hat, that is 0, because w1 is white, it does not depend on anybody else. So m naught I already know at time 0, x naught hat I already know coming from time 0. So given x naught, the best forecast I can make at time 1 is m naught x naught hat. So now this error is going to, this prediction is going to be an error. So x1 is the actual state, x1f is the predicted state. The difference is called the error in prediction, E1f. Superscript f always refers to forecast or predicted quantities, hat always refers to analysis quantities. So I am now going to get an expression for E1f that is equal to, so x1 is equal to m naught x naught plus w1, x1f is equal to m naught x naught hat. So if I substitute and simplify, I get this, but by definition this is equal to E naught. So now I get a recurrence relation for the evolution of the forecast error. Now look at this, it's a beautiful expression. The forecast error at time 1 is m naught times the analysis error at time 0 plus w1. The analysis error in the previous step is going to dictate the forecast error the next step. That is how the analysis and the forecast are related. Okay, now I would like to combine. So analysis is filtering. Analysis at the given time, forecast is prediction. So we have talked about smoothing, prediction and filtering. So in this process I already have filtering and prediction, part of 2. So you can think of E naught hat is the filtered estimate, E1f is called the forecast estimate, that is the predicted estimate, errors and so on. I hope this is clear. This is where the rubber meets the road. We need to combine several things in here. So what is P1? P1 is the analysis, I am sorry, the forecast covariance at time 1. So let us go back in here. This is 0, this is 1, I had x naught hat, I had p naught hat is equal to p naught, I have x1, I have x1f, I have to have p1f. I already know this is equal to m0 of x naught hat. Now I need to compute what this one is. If you understand this step, the step of going from k to k plus 1 will become trivial. So pk plus p1 of f is equal to E of E1 of f times E1 of f transpose. E1 of f from the previous page is this expression, that is that expression. There are 2 terms in each. If you multiply, there are going to be 4 terms. We already know the error in the analysis in the previous step on W1. So the error in the analysis E naught 0 in this step and W1, these are uncorrelated. Therefore of the 4 terms, the 2 of the terms will die because of this uncorrelated nature, as well as W1 is mean 0. I am left with only 2 quantities. The 2 quantities are related by this. So because we are doing this for the first time, let me try to write this down. So what is this? This is equal to m naught E naught hat transpose m naught transpose plus W1 transpose plus m naught E naught hat W1 transpose plus W1 times E naught hat. I am sorry, I made a mistake, 1 second. You get W1 times E naught hat transpose m naught hat. You can readily see the multiplication of these 4 terms leads to these 4 quantities. I am going to think of expectation of the whole expectation of the whole is equal to expectation of the individual quantities. I am now going to distribute that E to every term. So that is equal to E of this plus E of this plus E of this term plus E of this term. Now m naught being a constant, it comes out. This is the previous analysis, this is the future noise, these are uncorrelated, so this product is equal to 0. M naught comes out, this is the next noise, this is the previous error, so this term is 0. This term is essentially the noise covariance Q1. This is essentially m naught E of E naught transpose, m naught transpose, and what is that? That is P naught. Therefore, we get the expression m naught P naught m naught transpose plus Q1. There are two things worthy of notice here. The prediction covariance at time, the predicted covariance at time 1 consists of two parts. For example, one part is the initial covariance magnified by the model. This is the initial covariance magnified by the model. The second one is the covariance that is introduced by the model noise. Are you all with me, please? That's important. You have to have an aha here. This is an aha moment. So if a model is stochastic dynamics, if the randomness are coming from two directions, Q1 is the uncertainty in the prediction coming out of the model noise. The first term is an uncertainty that comes from the initial condition noise, uncertainty in the initial condition. Therefore, the prediction has two sources of randomness from the initial condition and the forcing, and those two together additively contribute to the total covariance of the prediction. Why this is additive? Because we are assuming everything are uncorrelated. If there is correlation between E naught and W1, then there will be other terms that is coming to clobber this equation. The correlation will also try to increase the value. So why do we assume things are uncorrelated? Because I would like to have a plain, simple, elegant formulation, and that's nothing can be simpler, nothing can be more beautiful than this formulation. I hope you got the idea of going from step 1 as going from step 0 to step 1. Therefore, I now know the forecast, I now know the forecast covariance. Once I have a predicted, once I have a forecast, I can create mischief. What is the mischief? A forecast is the best estimate I can have of the state at time 1. I have the forward operator. Now I can use the forward operator and the predicted state to create what is called model predicted observation. So that is what it is. What is the expected value of Z1 given x1 is equal to xf? Z1 is already given to you from Z1 is given by mother nature, but I am interested in the conditional of Z1, expected value of Z1 with respect to x1 is equal to xf. That is what this is my condition of the knowledge. I would like to be able to get Z1 from the model is h1 x1 plus v1, x1 is equal to x1f. This is again conditional expectation of the linear operator. The conditional expectation of v1 given x1 is equal to x1 is 0. Therefore, the model predicted observation is h1 x1f. Again, I am assuming the model operator, the linear operator can be changing in time. So am I considering h or h of k? Am I considering m or m of k? It turns out the arithmetic, the algebra replacing by h by hk, m by mk are no different from keeping them time invariant. So without loss of generality, we will pull the time index all through. That's the idea. So now let us look at this now. This is the model predicted observation. So Z1 is the actual observation, this is the model predicted observation. So that is the error in the predicted value of the observation given the model state forecast. So the product of the two is going to give you V1 inverse V1, that is equal to R1 as it should be. R1 is the observational covariance error. So that is a check on what we are trying to do. So the basic, this is the basic idea I have already illustrated. So you gave me x0, you gave me x0 hat and p0 hat. You use my model, I use my W1 or model M1 W1, I created my forecast, I created my forecast covariance. As I do that, somebody is giving you observation and somebody is giving you the observational covariance. So I have two pieces of information in here. I would like to combine these two pieces of information to create an analysis and an analysis covariance at time 1. So combining these two to get this is called the filtering. Going from here to here is called prediction. All we have done is to finish the predictive part. We have not done yet the combination part. So this step is called the data assimilation step, DA step. This part is called the forecast step. So now you can imagine, I started with x0 hat, p0 hat, I made a forecast. Then I got the observation, I created the new analysis x1 hat, x2 hat, p1 hat. Then I am going to use the model to get x1 x2f p2f. Then I am going to get z2 r2. From these two I am going to get z2 hat p2 hat, and the system continues. That is a cycle, that is a sequential process. So where is the data assimilation step comes in? The data assimilation step comes in after the forecast is made. The forecast plays the role of a background. Observation is a new information. I am combining them. You can see the Bayesian point of view, and that is repeated. It is because of this we call it sequential. I think it is better to remind ourselves what do we do in 4D-var? In 4D-var we first decide a time horizon n. We get observations z1, z2, z3, zn. We get all the observations, then we try to fit all of them to be able to decide the best initial condition. Once we decide the best initial condition, then we run the model forward. Anything beyond n is called the forecast. That is what we do in 4D-var. In sequential we never look back, we keep only going forward. Sequential data assimilation is exactly what is being practiced in all forecast centers of the world these days. So sequential is in other words, I know what I know, I simply want to update given the new information to get the new analysis. So if I know how to go from 0 to 1, that is essentially the same step to go from k minus 1 to k to k plus 1 or k minus 1 to k. So what is the general step? Now that I have described the process of going from 0 to 1 very clearly, I can take liberty with some of the details in going from k minus 1 to k. So I have been given the analysis and the analysis covariance at time k minus 1. From these two, using the model M, I am going to create the forecast and the forecast covariance. These two are generated using the model equations. Observations come, I do the data assimilation part. It is here the data assimilation is done. So forecast, prediction, data assimilations, filtering. So prediction, filtering, are continued sequentially. This combination of prediction filtering somehow called Kalman filtering. So what is Kalman filtering? Kalman filtering is the process of the process that underlie assimilating data into a linear model when the observations are linear. So Kalman filter essentially assumes LQG. LQG. Kalman is in fact a master of the LQG world. He essentially he has done many wonderful things in control theory. Kalman filtering is only one aspect of his multifaceted contribution to control theory, but it is this Kalman filtering that is applicable in the geophysical domain, because in geophysical domain, since we are concerned with naturally occurring system, there is no way to control the naturally occurring. You can't control a hurricane, you can't control an earthquake, you cannot control the blowing out of a top of a mountain, a volcano. Natural occurring system we can only observe, we can only predict. But engineering occurring systems you can analyze, you can predict, you can design, you can control. So that is the fundamental difference between engineering approach to engineering problem and scientific approach to naturally occurring systems. So geologists, geophysicists and atmospheric science people are also interested in same kind of problems that engineers are interested. The only thing is engineers have an added advantage of being able to control, whereas in sciences you simply have to be able to predict. So for example, if there is going to be a hurricane, we cannot change the motion of a hurricane. Well, engineers have sometimes suggested, when at the time when the hurricane forms, why don't you just drop a bomb and dissipate it. This is typically an engineering idea. If you talk to an atmospheric scientist or anybody else, they will simply laugh at it and go. They won't even care to think of answering that. So engineer's mind is always, if you know that there is a danger, why don't we control it and prevent the danger from occurring. That is the engineering, that is how engineers are designed. But it is very difficult to be able to control naturally occurring systems. But that is why much of what Kalman has done is unknown other than the Kalman filtering, because the Kalman filtering is only one aspect of the engineering solution that he has developed is applicable to the data assimilation setup. In fact, Kalman did not call it data assimilation. In fact, the ultimate paradigm in data assimilation was stated by Kalman, is embodied in Kalman filtering. What is that? I have a stochastic dynamic model, I have observations, I would like to be able to sequentially keep updating and creating newer analysis from previous forecast and observation. So in my view, 1960-61, when Kalman published his paper called Kalman filtering, that is a forerunner of all the data assimilation systems known to mankind. For example, the 4D war came out only in the mid 80s. Kalman filter was applied to meteorological problems only in the early 80s. So Kalman filter as a solution to a data assimilation problem far earlier than many of the folks in geophysical world had imagined, dreamed. That is what I would like you to think about. Why? In the context of weather forecasting in 1960, what was the kind of tool they were using? They were still using successive approximation. There was no 4D war, there was no 3D war. All these things came much later. Even the Kalman filtering idea, for it to seep through the engineering scientific literature, it took well over 20 years. So in my view, Kalman filter is one of the earliest of the complete solution to the data assimilation problem in the context of linear stochastic models and linear of observations that are functions of the linear functions of the observation corrupted by noise. I hope the sequential aspect of the idea is clear now. So what is it I am now going to do? I am simply going to run through the mill. I have been given x hat k minus 1, p hat k minus 1. I am going to run through the model. So my forecast at time k, pull the analysis, this is the analysis, pull the analysis through the model, you get the forecast. Then you get the forecast error. If you have the forecast error, this is the expression for the forecast error. Then this is the forecast covariance, which is the product of these two terms. Because the cross term vanish, this is the expression for the forecast covariance. Look at this now, no data, only model. So I go from 0 to 1, I go from k minus 1 to k. So let us look at the computational aspects of this now. To be able to generate the forecast, I have to run the model. Running the model is essentially matrix vector multiplication, that is cheap. So this is going to be O(n) square. But let us compute, let us see what happens in the update of the forecast error covariance. Assume pk minus 1 is given. Pk minus 1 is a n by n matrix, M is a n by n matrix. So I have to do one matrix multiplication, another matrix multiplication. Each matrix multiplication is going to cost me O of n cube. This is going to cost me O of n cube. Then I have to add two matrices, that is going to cost me O of n square. So which is the most expensive part in Kalman filter equation? It is not the forecast, it is updating the forecast error covariance. Updating the forecast error covariance is of the complexity of the order of n cube. You please remember that we did. If you want to multiply two matrices of each size 1 million on a teraflop machine, it took about 12.5–13 days. We have already examined that. So this multiplication will take 13 days, this multiplication will take 13 days, and this is probably several hours. We are talking about a month's time, and that is only to do the forecast error covariance. So what does it mean? For large systems where the state of the system is the order of 10 to the power 6 or higher, while I know what to do in Kalman filters, it is impractical to get it done in practice because of the curse of dimensionality. Such problems in computing field is called infeasible. It is not that I do not know how to solve, I do know how to solve. It is simply that with the kind of environment, computing environment I have, I cannot finish this. What is the added outcome of this? This promotes an idea telling computer folks, you need to build me larger machines. So originally it was megaflop machines, then it was a teraflop machines, then it became petaflop machines. Petaflop machines are 10 to the power of 15. There are very few petaflop machines around the world. Now they are talking about exascale machines where the flop rating is 10 to the power of 18. 18 flops. Japan, China, I am sure India also has joined this race, America. So almost all the wealthy countries in the world, the government related in the wealthy countries in the world, they are putting enormous resources in the development of faster and faster computers, because it is the availability of faster and faster computers that are going to be useful in making major technological innovations in the future. So weather forecasting in this sense is one of the hardest computational problem, not because we do not know how to solve, but because we do not have powerful enough computers to support us to be able to perform large computations in a short time. So that's a aside story that coming out of this. The impetus to deal with larger computers essentially come from these kinds of arguments. Again, I am going to quickly run through some of the things which I have already talked about from going from 0 to 1. So the conditional expectation of zk given the forecast is this. I can talk about the covariance of zk given xk. Now please understand, everything is conditional. Why? I am conditioning everything on the amount of information that is available. What are the information available? One coming from the model, another coming from the observation. So everything is a conditional analysis. Everything is a conditional analysis. So what is the data assimilation step? Okay, now I would like to be able to come back to the data assimilation step. You go back. I'm sorry, I can do it here. So what is the data assimilation step? I want to cut through the mess and give you. So this is k minus 1, this is k, I had xk minus 1, I had pk minus 1, I have xkf, I have pkf, I have zk, I have rk. I am going to combine the two to get xk hat and pk hat. So this is the analysis, that is the forecast, that is the observation. So what is it I am now trying to do? Please go back. We already have we know a lot of things. We already have done the static Kalman filter. Now do you see this is the static Kalman filter? Look at this now. I have the forecast xkf and its covariance. I have observation and its covariance. So what is it I can do? I want to be able to combine them. I can combine them in the Bayesian way. I can combine them in the linear minimum variance way. I can combine them as a 3D war way. We have seen all of them. Almost all these earlier experience leads to the fact the analysis at time k is equal to the forecast at time k plus zk minus hk times xkf. What is hk times xkf? That is the model predicted observation. What is zk? Is the actual observation. Are you with me, please? If you have a model, I should be able to predict everything. You should never be afraid of prediction. The prediction may come true, prediction may be a bust. If the difference is large, prediction is a bust. Even though the prediction is a bust, I am learning something. So z minus hk xkf is the innovation, is the new information that the observation brought to fore that I couldn't have known at the time when I made a prediction. So I am going to combine the forecast with the innovation. The coefficient of linear combination is a matrix K. K is called the Kalman gain matrix. K is a rectangular matrix of size or n by n. So what is that we have done? We have made the best forecast. I hope you understand that. So xk f is the best forecast available. That is the best background information that is available to me. Now I need to estimate. So this is the estimator. This is the structure of the estimator. What is there? Is the linear structure. This can be written as, why this is the linear structure? Xk hat is equal to I minus kk hk xkf plus kk zk. Do you remember? This looks like L times xkf plus k times zk. So L is a matrix, K is a matrix. In this particular case, K is kk, L is this. So why am I bringing this? This is the linear. So the estimator is a linear structure. I would like this estimate to be unbiased. I would like this estimate to be minimum variance. So I am going to fall back on linear minimum variance estimation. Hey, that is exactly what Kalman did. And I don't have to do too much because I have already covered linear minimum variance estimation. So what is it I have done? I have essentially prepared all the concoctions needed. I simply need to mix them. It is like a fast food chain. In McDonald's, every order is met within 5 minutes. How do they do that? They anticipate a certain amount of sale. They try to prepare all the ingredients. The ingredients are already stored. Whenever an order comes, they simply need to assemble the already ready ingredients to make the product. So every product they can assemble in a short time. That is why this is called fast food chain. And that is the approach I have taken here. I have prepared all the concoctions that are needed to do the Kalman filtering. So what are the various things we did? We have talked about, given two pieces of information, one called background, another called observation, how to mix them. How many different ways in which we have looked at them? Bayesian way. We have looked at linear minimum variance way. We have talked about 3D war way. So I have all kinds of concoctions ready, and now I am facing the problem. I can simply call any one of these framework and be able to solve the problem. So I now know from the theory we have already talked about how to determine kk. We already have the formula from Gauss to Kalman, one of the modules we have seen. From Gauss to Kalman for one of the modules we have seen. So this gives rise to, I am simply trying to remind ourselves, this is the forecast value, this is the observation, this is the actual model. So for true state, forecast, observations, and the Kalman filter equations. And also I would like you to understand the forecast, the analysis feeds into forecast, and the forecast feeds into analysis. Look at that now. The previous analysis provides the next forecast. The current forecast and the new observation decides the current analysis. That is filtering. So this is the filtering step. I hope you enjoy. This is the forecast step. Oh, I already have it here. So the whole question is, my analysis of the linear function of the forecast and the observation, the linear function of the forecast and observation, I would like to be able to one more. So I will erase this part. You already know this part. Therefore, what is involved in here? I already know I already know HK. So the only thing I need to determine is KK. Linear structure is involved. I only need to be able to compute the covariance of xk hat. The covariance of xk hat is going to be a function of kk. I am going to minimize the trace of the covariance with respect to the elements of kk. That is the minimum variance estimation. I have already talked about the methodology for doing this in the previous class. So I have earned the right to quote the results. But again, even instead of simply quoting, I am trying to plow you through the various steps. I am not okay. Let me quickly tell you the various steps. I am not. So this is the analysis structure. I already know from the previous step how the variables in time k are related to variables in time k minus 1. So I am relating this to I'm sorry, I'm jumping. I'm relating these to variables in time k plus 1 from k to k minus 1. K to k minus 1. I'm having the error. I substitute the error in here. I get the structure of the analysis error. So this is a structure of the analysis error. Now please understand, the structure of the analysis error involves the Kalman gain. I have not determined Kalman gain. I have only talked about what is that. Therefore the analysis covariance is given by this structure, and I have to be able to okay. So if you do these and simplify, sorry. So I hope you got these structures again as a, yes, it's easy for me to do this because look at this now. EK is a sum of 3 terms, 1, 2 and 3. So there are going to be 6 terms when you multiply in PK. If you carefully analyze these terms and simplify, you get your PK to be this expression. This is the ultimate expression. DK comes in here. Please recall, this is exactly the expression we have done in one of the earlier modules. This is the term which is quadratic in K. This is linear in K. This is the linear in K. I need to be able to minimize the trace of PK with respect to KK. KK has NM elements. The conditions for the Kalman gain, minimization of the total variance, we have already done. And that analysis, I am now quoting the optimal Kalman gain is given by this, So now I have computed the optimal gain. Once I compute the optimal gain, I wanted to go back. The optimal gain depends on KK. So I know the value of KK. So if I substituted the optimal gain value in here, I get the minimum expression for the minimum value of the analysis covariance. The minimum expression for the minimum value of the analysis covariance is given by this, which can also be rewritten like this. Yes, there is ton of algebra to be done. I'm assuming you will do the algebra and not only do the algebra but enjoy the lessons coming out of this algebra. Is a very educative algebra, as any other algebra is. So the expression for the Kalman gain is given by this. The expression for the optimal covariance analysis covariance is given by this. So I have completed the Kalman filter equations. So what is that now we have said? Let me do it once more in here. I know some of you might feel that I have gone a little faster, but there is nothing I have done here is new. I have already built everything in here. So if I am going from k minus 1 to k, I know how to compute x hat and pk hat. So that's the Kalman filter equations. We summarize this Kalman filter equation in a tabular form little later. Before that, we are going to provide several comments relating to the structure of the Kalman gain